What's up, Breakthrough? For those of you who don't know me, my name is Janet and I am the 8th grade science teacher. Welcome to my elective on black holes and gravitational waves. These are two topics that I find really interesting and I've been learning a lot about lately. So today I thought that I would share some of what I've learned with you all. If you want to learn more about these super cool natural phenomenons, then keep on watching.
Space is a pretty dark place. Even so, some areas are darker than others. Nothing is darker than a black hole. A black hole is an area of such immense gravity that nothing, not even light, can escape from it.
So we're going to pause right there because she said gravity. And in order to understand what a black hole is and also what gravitational waves are, we need to understand what the concept of gravity is. If we look at this text, it says that gravity is an attractive force that acts between any two objects which have mass. If we look at this picture here, you can see a grid, and that grid represents the fabric of space-time. One of the biggest takeaways from Einstein's theory of general relativity is that space isn't just a fixed entity, but rather it's a constantly changing, constantly moving fabric that gets distorted by the presence of massive objects. As you can see, the ball with the most mass, the yellow ball, distorts that fabric more than the red or the orange balls because it has more mass. If we take a look at this picture, you can see how the smaller ball, which is the moon, is falling in closer to Earth because Earth distorts the fabric of space-time because it has lots of mass compared to the moon. This is the same reason why we can't fall off the Earth or float away. It's because the Earth's gravity pulls us back.
Black holes form at the end of some stars' lives. The energy that held the star together disappears and it collapses in on itself, producing a magnificent explosion. Here's where things get crazy. All of that material left over from the explosion, many times the mass of our sun, falls into an infinitely small point. Black holes can form in many ways, though, and large black holes can have tens to millions of times the mass of our sun trapped in a point smaller than the tip of a pin. Some black holes trap more and more material as their mass increases. The point where all that mass is trapped is called a singularity. It may be infinitely small, but its influence is enormous. Imagine a circle with a singularity in the middle. The gravity on the inside of the circle is so strong that nothing can escape. It sucks in everything, even light. That's why it's black. This circle is known as the event horizon. An event horizon is probably what you are thinking of when you think of a black hole. What would happen, you might wonder, if we took a spacecraft near a black hole's event horizon? The answer? Spaghettification. That's the technical term, at least. As our spacecraft approaches, the gravity will be so much stronger on the side closer to the black hole than at the other side that it will get completely stretched out like a piece of spaghetti. Try as you may, you would be hard-pressed to find anything weirder or cooler than a black hole. Presented by NASA's Space Place.
Thank you, NASA Space Place, for that very informative video. At the end of the video, they gave you the challenge of finding something weirder or cooler than a black hole, and I think I have the answer. What's cooler than one black hole, you might ask? Two black holes, or more specifically, what happens when two black holes collide? When two black holes collide, they produce a phenomenon called gravitational waves, which we're going to learn more. So as we talked about before, Einstein's theory of general relativity describes how massive objects cause a distortion of space-time. So if you look at the image on the left, you can see that the smaller ball is pulled in by the bigger ball because the bigger ball distorts the fabric of space-time and it falls into that gravity well. So black hole collisions occur when two black holes come close to each other, and they feel the gravitational force of one another because, recall, black holes are very, very massive, very dense objects. So when they come together and collide, it results in one of the most cataclysmic events in the cosmos. And the two black holes form into a new, larger black hole. The mass of the new black hole is slightly less than the combined mass because some of the mass is converted into energy, and it releases something called gravitational waves. Gravitational waves travel at the speed of light, which is 186,000 miles per second. Unlike sound, gravitational waves can travel through a vacuum. They can travel through nothing. They have properties of both transverse and longitudinal waves, which means that they stretch things in two directions. But scientists can only detect transverse waves. Gravitational waves actually are produced by every object with mass. However, gravity is such a weak force compared to the other forces that we experience. So only very heavy, accelerating objects produce detectable gravitational waves. Gravitational waves can have a wavelength of anywhere from 1 kilometer to the span of the entire universe. Scientists can tell that gravitational waves exist because of LIGO, which stands for Laser Interferometer Gravitational Wave Observatory. You might be thinking, what the heck? Because that sounds like gibberish. But basically, it is just the fancy name of a lab that scientists built to detect these waves. And it has 4-kilometer long tunnels, and I'm going to show a video that explains what is inside the tunnels and how they work.
To measure this stretching and squeezing, Ray turned to a device called an interferometer. A laser beam is split and sent down a pair of long perpendicular tubes, each precisely the same length. The two beams bounce off mirrors and recombine back at the base. The light waves come back lined up in such a way that they cancel each other out.
And you add them together, you get nothing. You get a zero, a big fat zero. No light gets detected at the photodetector.
But when a gravity wave comes along, it distorts space and changes the distance between the mirrors. One arm becomes a little longer, the other a little shorter. An instant later, they switch. This back and forth stretching and squeezing happens over and over until the wave has passed. As the distances change, so does the alignment between the peaks and valleys of the two returning light waves, and the light waves no longer cancel each other out when added together in the recombined beam. Now some light does reach the detector, with an intensity that varies as the distance between the mirrors varies. Measure that intensity, and you're measuring gravity waves.
The light takes longer time in here than it did in this arm. Now it takes a shorter time, and these things don't cancel so beautifully anymore.
So I know that might have been kind of confusing, but essentially what LIGO does is that when gravitational waves pass through Earth and they stretch and compress and expand the space that we're living in, the paths of the two lasers no longer line up perfectly as they would be if there was no gravitational wave, and that is how scientists have confirmed that gravitational waves do in fact exist. So that brings us to the end of our content for this elective, and if you made it this far in the video, I would first like to applaud you for sticking with it. I know that I kind of threw a lot of new concepts at you right away, and there was a lot of stuff that might have been a little confusing, so great job for sticking with it. If this is a topic that you are interested in, I will put some recommendations of videos and such to watch on this screen, and I will also link them in the description box of the YouTube video. And I would encourage you all to keep watching videos, keep watching movies, keep reading about this stuff because it is super interesting and there's tons to learn. So to prove that you completed this elective on gravitational waves and black holes, I would like you to send an email to the Breakthrough Electives email address, which I will put right here, and send 2 things that you learned. And also, just like for me personally, if there is something that you're interested in or you want to talk about, or you have a suggestion of a topic that you want to see me explain in a future elective, please send me a text, shoot me an email. My contact information will be right here. And I look forward to hearing from all of you, and thanks for watching.